Non-standard normal distributions still follow a bell-shaped pattern, and the only real difference is that they have a mean and standard deviation that are different from 0 and 1, and we're now working with x values as opposed to z-scores. The other thing with these is that we will still be rounding to 2 decimals, and when we're working with non-standard normal distributions, we will not be converting these values to z-scores as you might see in other videos online, because converting to z-scores first yields a large rounding error. So in order to give a more accurate probability, we are going to use our calculator features of I and V norm and normal CDF, utilizing the current mean and standard deviation of our data set to yield a more accurate probability. Let's look at this example using the U.S. Air Force, which requires pilots to have heights between 67.2 and 73.2 inches. And this is so that they'll fit correctly in the cockpit of the planes. Through medical records, it's been found that pilots have a mean height of 68.6 inches and a standard deviation of 2.8 inches. First, we want to find the percentage of pilots that meet the height restrictions. If we first create a picture of our bell-shaped curve, we can label with our mean and our standard deviation, requiring us to always enter in the units when we're recreating our pictures. Next, thinking about our number line, our first value or our lowest value is 67.2 inches, which is to the left of our mean. The upper height is 73.2 inches, which is to the right of our mean. The question is asking us to find a percentage, which is first our probability giving us the decimal value that represents an area that we can then turn into a percentage. We're going to find the probability that a pilot's height is between 67.2 inches and 73.2 inches. Finding probability uses the normal CDF feature. Since my lowest and highest values of heights are given in a range, and my mean and my standard deviation are also given, I can enter all of those values in my normal CDF. As a probability decimal value, this gives me 0.6413. I can then turn that into a percentage. Moving the decimal point over 2 places to the right and adding a percent symbol, the number or the percentage of pilots that meet their current height restrictions is 64.13%. If the Air Force wants to include more women pilots in their programs and have changed the height restrictions to exclude the tallest 2.5 and the shortest 2.5% of pilots, what are the new height restrictions? If we think about a picture where our mean and standard deviation are still the same, that means that we're now looking for the x values that are trying to be our cutoff points to throw out the lowest 2.5 and the highest 2.5 of pilots. Since we're dealing with a height restriction, the new shortest height, this is going to be an x value using I and V norm. Again, our area to the left of this value is 0.025, taking 2.5% and moving the decimal 2 places to the left, with our mean and standard deviation. Our new shortest height is going to be 63.11 inches. For the tallest height, again, we're working with an x value and I and V norm. To find the area to the left that I need to use in my calculator feature, I need to think about the full 100% or the probability is equal to 1 and subtract off that probability or area to the right. So 1 minus 0.025 is 0.975. That gives us a new tallest height of 74.09 inches. Remember that when you're adding up the entire area of the curve, it equals 100% or a total of 1. So the area to the left here and the area to the left here when we're finding the shortest and tallest height will be equal to 1.